All right. I'm back. I had to stream a little earlier, but I kept getting interrupted, so I'm just going to start over. We're looking at 59. It relates partly, evidently, to this function in 57. So previously, we had defined this function, q over 1 minus q times 1 minus z, plus q squared over 1 minus q squared, 1 minus z times 1 minus qz, right, etc. So back then, they mentioned that it satisfies this equation. 59 says, prove its identity. Which, at first glance, has nothing really to do with our function, perhaps. But he does say a hint is that g of q to the negative n is negative n. So evidently we're meant to use this function to represent the left-hand side. But then he says use it to derive the power series of negative log of 1 minus x. So that's the part that I haven't talked about yet. But I'm just going to start over from the top anyway. So I think we're trying to prove is something like something like that. So the one thing to notice, there's two parts to this. The g function is like that. You could write it as a sum. I guess I'll just do k. Okay, we're going to start at 1. And then the function that's here, you get 1 minus z, but you continue to get these 1 minus qz's up until q to the k minus 1. So if k is 2, right, we're stopping at, well, if k is 2, the last factor is q to the k minus 1, like that. So this does kind of remind us of this. See the 1 minus q to the k downstairs. It looks almost the same. All he's going to do is let a be q inverse, and then sort of rewrite this sum. And we're going to look at g of q to the negative n. Now it's kind of hard to see it from, well, you can see that it's finite, right? If you plug in q to the negative n, you'll see that at some point you get a 0 here, right? At some point n equals the power, and you get 0. And so all that factor, that term and all terms of higher order are 0 in your series here. So you can see this is finite. It's actually of degree n. But this actually equals negative n because, first of all, g of q inverse equals negative 1. Like if you plug in q inverse here, second term is 0, so are all the rest of the terms. But the first one you get that, which when you distribute is just negative 1. The other thing is, from one of the previous problems, well, from 57 itself actually, from the first problem involving this function, he mentions a functional equation. And so if you plug q to the negative n in for z here, in this, effectively this identity for the function g, the right-hand side will eventually be 0. One of these terms will be 0. You get 1 minus q. So say you plug in q to the negative 3. This factor is 0, which means the whole right-hand side is 0. So when we evaluate at q to the negative n, you're just going to get this stuff equals 0. You get a statement like, and this one was qz, so in our case it's like that, but it equals 0. So the difference between these two guys is 1. Or I suppose you could flip this around. You could say, if you're trying to see a formula for q to the negative n, it's equal to whatever formula you have for negative n minus 1, and then just subtract 1 from it. So since we know that at negative 1 you get negative 1, we know it's true for, what is that, 2? We could see that it's true for, actually he mentions that it's true for 0 as well. G of 1 is going to be 0, he mentions. You can see just from the definition, if you plug in 1, but I don't know if that's really necessary for us to mention it. The point is, for n equal to 1, this is true, right? And so by induction, we can just sort of iterate this, right? You're seeing how this eventually gets down to g q inverse. So if we knew that this was equal to the negative of n minus 1, then this works out to be negative n. So that's it by induction, why this is true. And then the other thing is, for this 59 problem, the second part of it is that if you write your function like this, you can kind of see the numerator there. So first of all, when we plug in, so now I'm using the actual, this definition, you know, like this series representation of g. But we're going to plug in q to the negative n instead. You're going to get this stuff, q to the negative n, and like we were saying, if k equals n, that's the last factor you're going to see, is this one, right? As soon as you plug in k equals n plus 1, you get 1 minus q to the n, right? You get q to the n times q to the negative n. So you're getting 1 minus 1 there. So there's no reason to ever put n plus 1 here. It's actually just the sum up to n. And then we get q to the k, 1 minus q to the k, and then we get these terms like 1 minus q to the negative n, 1 minus 1 smaller than that, right, because we're multiplying by q, so you get sort of negative n plus 1, up to 1 minus q, and it stops at, well, it stops at k minus 1 times q to the negative n, so you're getting negative n plus this quantity, like that. Now, you can sort of divide this, like factor q to the k out of the denominator here. in fact, maybe I'll just do that separately. We're going to do two things. We're going to let A be, did I write it? Here it is. We're going to let A be Q inverse. So first of all, let A be 1 over Q. And then the other thing is, if you factor Q to the K out here, you're getting something like 1 over, like you're getting that. Here's another form for this guy. Right? Which is A, or A to the negative K, right? It's the negative of. So if I put a negative here, we can reverse this order. We'll get 1 over 1 minus A to the K. Right? That's that coefficient. And then we've got these factors, which I'm replacing with A's. So this is now 1 minus A to the negative N. Sorry, A to the N. There we go. 1 minus, I want to say N minus 1, right? And we stop at the negative of this, N minus K plus 1. And that should look familiar. So that's how you get from this definition of G to this left-hand side and the right-hand side. He basically told us that. I mean, he says it right there. So what he writes right there is basically the whole answer for 57, or 59. But he has a follow-up comment that I'm about to struggle with. So he says, once you've proven this part, right? So we just did that. We're basically done with 59. But then he has a little secondary comment here. He says, use it to derive the power series of negative log 1 minus x. And so that's what I was gonna. So that's it for the bulk of 59. But how does that relate to negative log 1 minus x? I looked at it the other day. It was, I don't know. I was never any good with these like random substitutions. You know what I mean? Like sometimes they'll just do a substitution, puts it in a totally different space, and suddenly the problem is really easy. I think what's happening is they're saying like, well, it looks kind of like this, and they run through and they see that it works, and then they go back and figure out what substitution would make that happen. Anyway, I still don't quite see how one would get from here to negative, like, right? Like, see this and be like, oh, that's just the power series for log. I don't know, man. But the funny thing is he's kind of going backwards. Like, we use the G series to get this form, and now we're going to undo it. We're going to put it back in terms of Q just to get this result with the log thing. So this is the correct substitution to do, but I was trying to see if I could figure this out on my own without, somehow use this result along with this to get this series for log. So yeah, wish me luck. We're going to have some scribbles here that probably going to struggle with it a bit. Yeah, so anyway, actually, you know what? First, thing immediately is solve for Q, right? I get 1 minus y over n. So do I want to take the reciprocal of this? Because A is definitely the reciprocal of this. I kind of want to keep this form, right? Because I can see that if you take a limit of that, you're getting e to the y. Does that help us? If this was, no. Well, anyway. This was n. We know that. So what happens if I look at these? Like if I undo this, if I do this substitution, Q inverses A. I just feel weird about this. This is definitely Q. All right. 1 minus. I feel pretty dirty putting this in parentheses and writing a negative n above it. Um, is that going to work out for me? You can see that I do like raising this to n. I'm just a little nervous about. Like, well, what's the problem? It's fine. It's going to be the reciprocal, so we'll get a negative in there, which is maybe fine. Maybe that's good. I'm just noticing q to the n tends to e to the y, right? Um, hmm. Yeah, all right. I guess we'll try it. Yeah, I just don't see it happening. I don't really follow what I'm doing. I think I'm missing the point. So it's still true that this stuff equals n, the sum of this stuff. Um, hmm. Isn't this usually a plus? Yeah. Am I wrong about this? This is supposed to be a minus, isn't it? This is e to the negative y, isn't it? I mean, yeah, it is, right? Um, yeah, I'm sort of falling apart here. All right, I'm gonna go ahead and look. Um, yeah, I feel like I'm missing the point. I somehow got the right. I used the right substitution, but I still got the wrong. Q is 1 minus y over n, right? So this is where he ends up, you know. So we have this. Oh, he's doing something clever here. Okay, so that's how he dealt with the 1 minus q to the k downstairs. He multiplied on both sides by 1 minus q to give himself this series downstairs. Um, and then as n goes to infinity, q goes to 1. This actually cancels on the right, and you get negative y. Anyway, you see what I mean? This is like, it feels pretty obscure to me. Which is a shame, because I could see this maybe having applications. Like, sometimes you want a power series for a function, and maybe it's difficult to just use typical Taylor series stuff. But this is over my head a bit. I mean, I just never would have thought to do do this trick, and then boom, take a limit. Anyway, let's keep chugging away on this one. So obviously we have the stuff in the brackets. We've got negative n, and I would not have thought of this, but I can explain it. When you have, well, here, he stops at k minus 1, see? So if you had, say, 1 minus q to the k over 1 minus q, this is this geometric series. This is extremely common. We have this, but it's in the denominator. So to force this to happen in the denominator, so he didn't keep this here. He replaced you know, we had this in the denominator. Right? Yeah. Do we have an a in the denominator? Well, yeah, we have a negative. We have a negative. So he does two things. He undoes that. I guess I could have left it the way it was, huh? Oy vey. He does that, and he negates both sides. And then he multiplies by this missing term. If you look on the right hand side, he's got 1 minus q. So the negative of 1 minus q to match up with this guy. So if you took yeah, if you took the negative of, I don't know why he phrased it that way, but negative 1 minus q would be q minus 1. Okay? So here's the original denominator. This is the same thing. But the whole reason he's doing that is that now this whole thing is q to the k over this series, this finite series. Like that. So that's your coefficient. Well, these guys are still there in the numerator, but this guy downstairs has become this stuff. So he's got negative 1 minus q times n is the sum that we had. All right? And instead of this denominator, he's replacing it with this stuff. Of course, his q is this 1 minus y to the n. Then you got this numerator, 1 minus q to the negative n, etc. And now we should be able to just take a limit. Also notice that you can solve for this on the left-hand side. You're going to get y, I presume. Oh, yeah, right, it's right here. It's the negative of y. So y is defined to be the negative of this. So something tells me he like started here when he did this, when he set up this problem. He like somehow went from the answer to here and then was like, oh yeah, okay, I'll let y be this junk. Here's my function right here, the negative of y. Anyway, so without even taking a limit, this is negative y. On the right-hand side, if you take a limit, q tends to 1. I mean, q on its own tends to 1. For a fixed y. So yeah, basically he just takes a limit now, and the answer should pop out. But what are we seeing exactly? It's 1 minus e to the y, right? I think. Yeah. Did I miss a k somehow? This is the part on top. The bottom, since q goes to 1, you're getting k for that part. But what happens to all these guys? Do each of those become, well, here. So what he's saying is you're getting this sum. I'll just jot that down. So for a fixed y, we're getting negative y is the sum of it's just k downstairs, right? 1 plus 1 plus 1 k times. Upstairs you get like 1 minus e to the y to the k. So yeah, there's a little more going on. I think this distributed, so you get, right? You can afford to distribute this q to everything. Anyway, I'm pretty sure this is 1 minus e to the y, yep, to the k. So I'm just trying to make sense of that. Denominator we got. Is it really just like this simple? This is 1 minus e to the y, and you have k factors of them. And this guy just goes to 1. So yeah, you have k factors of something that looks like 1 minus e to the y. Even for like small k, this n is increasing. So they have an n in the power for every single one of these factors. So that kind of makes sense that the limit is e to the y, just from the definition here. So q on its own, for like a small power, right, that goes to 1. But Yeah, does that make sense? Each one of these, though, goes to 1 minus e to the y. So like even this one looks like it has some extra terms, but it just times some fixed q to the k for some finite k, right? This n is much larger than that. So we're using the fact that q to the negative n goes to e to the y. So that's where you're getting your k factors of 1 minus e to the y. And then you can see here this is 1 minus stuff to the k. Like this is your typical power series for log of 1 minus, well, yeah, log of 1 minus x, right? So we're clearly letting this happen. Huh. Actually, you usually do this at 0. So this is x. So that y is log of 1 minus x. That's what I meant.